So it turns out there are a wide variety of trigonometric functions to integrate. So remember that when you differentiate sine, cos, tan, and sec, you get these results respectively as listed on the screen. So let's talk about our next area in integration, which is integrating powers of sine. So if we have like powers of sine and powers of cos multiplied together, the trick is if your power of cos is odd, pull out the cos and use your substitution u equals sine x. Like pull out one of the causes so you can get a cos dx. So when you use u equals sine x, when you get du dx, it becomes cos x. So du is equal to cos x dx. So pull out the cos and use u equals sine x. If your power of sine is odd, pull out that sine, then use u equals cos x. So basically, whichever one is odd, you can pull that one out, then use a substitution for the other one. It makes more sense why we do that when we do a question. And afterwards, you can use like trig identities to help solve. But if you're not lucky and you don't get any odd powers, you might have to just use double angle formulas, like either the sine double angle formula or the cos double angle formulas by rearranging using that. But it can be brutal and it can be a bit of an algebraic nightmare. But sometimes you might get a question where it's in the context of a reduction formula, which will help in the third case. And we'll be talking about reduction formulas at the end of today's lecture. So let's look at integrating powers of sine and cos now. So let's say we got the integral of sine to the power 6, cosine to the power 5, x. So sine x to the power 6 times cos x to the power of 5. So in this case, what you would have done, notice how the cos x is the one with the odd power. So you can just break it down into, as listed on the slide, pull out one of them. So you get a cos x dx. So you'll get a sine to the power 6x. Then we're left with a cos to the power of 4. And then you can just use your substitution u equals sine x. So this will become, in terms of u, here, this is the same thing as cos squared x, which squared, so then you can just use your trig identities for that. So basically, and then when you do du dx equals sine x, you get that du is equal to sine x dx. So this cos x dx becomes a du. Then we get u to the power 6 times 1 minus u squared. And then afterwards, you can basically expand the brackets. And then you can integrate like normal, then replace the u's with signs. So that is an example of how we can integrate sine to the power 6x cos to the power 5 x. Like you'll get this result. So yeah, this is an illustration. And of course, if sine was odd, you would pull out a sine and then you let u be equal to cos instead. So yeah, it's a really useful trick for when you have to deal with powers of, when you have to deal with high powers of sine and cosine multiplied together. Okay, this is a classic, how we integrate tan. Well, this is pretty easy. Just remember that tan is the same thing as sine over cos. And remember that the derivative of cosine is negative sign. So we want to make sure we have a negative sign in the front. So you can put a negative, but also put a negative at the front so you're not changing the question. And then this is in that beautiful form we love where we've got 1 over f of x, but it's being multiplied with the derivative of the function inside. So you can directly, when you integrate this will become ln absolute value of that function. So it's going to be here negative ln absolute value of cos x plus c. So how do we integrate sec? Well, there's a trick to this. It's kind of hard to integrate it without knowing the trick. But basically the trick is, if you're trying to integrate sec, the trick is you want to multiply with sec x plus tan x and divide by sec x plus tan x. So you're not changing the question. So these will cancel out. But this is the trick of what you have to do. The reason why we do this is because this will become sec squared x plus sec x tan x over sec x plus tan x. And the thing is, the derivative of sec x is sec x plus tan x. The derivative of tan x is sec x squared. So basically, this is also in the form of having f dash of x over f of x. Because the derivative of sec x plus tan x is simply just going to be sec x tan x. It's going to be sec x tan x plus sec squared x, which is what we have here. So this will actually give us, when we integrate ln absolute value of sec x plus tan x plus c. And that's how we integrate sec x. You just have to know this trick of multiplying the top with sec x plus tan x and the bottom with sec x plus tan x. So you can see it here. That's how we do the integral of sec x. And if we're integrating powers of sec and tan, same sort of guiding principle. So if your power of sec is even, you can pull out a sec squared and then use the substitution u equals tan x so that you can get a sec squared x. Because remember, the derivative of tan is sec. So you can do some manipulation with that. If your power of sec is odd, and n is also odd as well, you can pull out sec x tan x from the integral, then substitute u equals sec x, because we know the derivative of that is going to be sec x tan x. Otherwise, try to convert everything in terms of sec using this identity, then try doing integration by parts. But that's a really horrible case, which hopefully you won't get. So here's an example of what I mean by that. So if we're integrating sec to the power of 4 and tan x to the power of n, where n is a positive integer. Here, because we know that sec is, the power of sec is even, we can let u equals tan x. We rearrange to get du is equal to that. We pull out a sec squared x, it'll become that using that, and then you can just integrate like normal, and it'll all work out like that. And it helps with this identity that the one with the tan is sexy, so 1 plus tan squared x is equal to sec squared x. And here's an example where they're both odd. So instead you let u equals sec x. So then therefore, when you differentiate, you get du is equal to sec x tan x. Then you can pull that out from there. And then you can just keep resolving it, and then you can solve it. And here, if it's just sec and it's all odd, you can try breaking it into 2 and then use integration by parts. So notice how we've strategically split it into sec x and sec x squared, because we know that we can integrate sec x squared quite easily. So in red, this is our v dash. When we integrate, it will become tan x. And here with sec, when that's going to be our u, so the u dash of sec is sec x tan x. So you can apply that, and then you can be on your merry way to, it will be sec x tan x times tan. So then you can keep doing that. So then once you get this integral, you're going to have to, you can change this into in terms of sec. And what actually happens is you actually end up getting this sec x cubed again. So you actually need to take it to the other side, because remember we said we let I be equal to sec cubed x. So along our way of working, we got sec x tan x using integration by parts. We got a sec cubed x plus integral of sec x. Now the thing is here, this is going to be I. So it's actually going to be sec x tan x minus I plus integral of sec x. So you can actually take that to the other side. So you could say that 2I is equal to sec x tan x plus integral of sec x. And we just talked about how we integrate sec x. We simply, we know that this is going to be ln absolute value of sec x plus tan x using the process I explained earlier. And then don't forget, it's an indefinite integral process, so we can do a plus c. But in this case, we notice how here we got a 2I. So when we simplify I to get what, remember we let I be equal to sec cubed x. So remember, c is just any arbitrary constant. So you, for the sake of making your life easier, you could just do a plus 2c because it's just any arbitrary constant. So therefore, when you finally find what I is, which is integral of sec cubed x, it's going to be half sec x tan x. You can factorize it, or you could just expand it. So half ln sec x plus tan x plus c. So that you could just have a final c at the end. So yeah, this is your answer. Here on the slides, it's been factorized the half, but here I've expanded the half. But yeah, what's with this random plus c plus 2c? It's literally just as a matter of convenience. Remember, c is just any arbitrary constant, so you could make it whatever you want, just so that when you divide by 2, just it's a nice c. So you can see this is a typical extension 2 sort of technique, where in the process of integrating, you actually get the original integral back in your working, which means that you have to actually take it to the other side so that you can actually get what the actual integral is. So sometimes when you integrate, it's also useful to use your product to sum identities that you learned from extension 1 in year 11, and that will help you integrate when you have sine A times cos A as well. So, or like cos A times cos B, sine A, sine B. So for example, if you're asked to integrate sine 3x cos 4x, just remember your product to sum identities from year 11, and then you can integrate like so. Another way you can integrate is, remember when you learn about the T formula in year 11 extension? Well, another application of the T formula is actually with, integration, because you can actually use, if you have like an integral which has sine and cos in the denominator or something like that, you can just let t be equal to tan x over 2, then use your trig your T formulas to replace it, and then it will help you do the integral. So remember, when you're differentiating that and you're making dx equals to 2t, always do everything from scratch. Basically, don't quote this result that you get when you use the T formula. So let's say we wanted to integrate 1 over 1 plus sine x plus cos x. So with respect to x, in this case, we can let t be equal to tan x over 2. And remember that it comes from this triangle that we could draw. So when we differentiate t with respect to x, we get sec squared x over 2 times 2, which is going to be, times half, I mean, because of the chain rule. So that's going to be half. Remember that sec squared is 1 plus tan squared. So I'm going to change the sec squared into 1 plus tan squared. So that's going to be 1 over 2. We said that t is equal to tan x over 2, so this is 1 plus t squared. So therefore, I could say that dt is equal to half 1 plus t squared whoops, I meant, yeah, this is dt over dx. That's going to be 1 plus t squared over 2. So therefore, when I flip it, dx dt, that's going to be 2 over 1 plus t squared. And hence dx is going to be 2 over 1 plus t squared dt. And now when I want to integrate this, I can simply change this all in terms of t. So 1 plus 2t over 1 minus t squared using the t formula, plus 1 minus t squared over 1 plus t squared. And the dx is going to be 2 over 1 plus t squared dt when I integrate. So that is going to be 2 over 1 plus t squared plus 2t plus 1 minus t squared. And that will cancel out. And I'm left with the integral of 2 over 2 plus 2t, which is going to be 1 over 1 plus t dt. And this is going to be ln absolute value of 1 plus t plus c. And remember that t is equal to tan x over 2. So this is ln absolute value of 1 plus tan x over 2 plus c. And that's how you would solve an integral like that, where you would have, when you asked to integrate 1 over 1 plus sine x plus cos x, you can just simply use the t formulas to help you do that. So it's a really useful trick for when you have like sine and cos being added in a denominator or something like that. So we are running short on time, so it's I'm going to have to sort of go through this content quicker than I would like to. But with these trigonometric substitutions, sometimes when we have like a square root of a squared minus x squared, or like x squared plus a squared or x squared minus a squared, a smart substitution you might have to do is using a trig substitution, because these will allow us to use Pythagorean trig identities to get rid of the square root. Because let's say if we had x equals a sine theta, this would be a squared sine squared theta, which would be when you factorize out a squared, it'll be 1 minus sine squared, which will give us cos squared. So it'll be the square root of a squared cos squared, which will give us a cos theta, which is much easier than having to deal with the square root. So here's an example, and yeah, the same logic goes with x squared plus a squared. If you substitute x equals a tan theta, you get like a 1 plus tan squared relationship, which will give you sec squared. And yeah, so let's say we had an integral like this. If you let x equals tan theta, you know that this thing in the bottom will become sec squared, which will become just sec, and that will cancel out with the sec that you get in the top because of what you did when you did the substitution. And then you can then integrate it like so. If you wanted to integrate root 9 minus x squared, you can let x equals 3 sine theta, and then you can proceed to integrate like that. But remember, the original thing was in terms of x, so you want to be careful. You have to draw a triangle to remember that your relationship is that x equals 3 sine theta. So we know that sine theta is equal to x over 3. So you would just draw a triangle like this where x is equal to opposite over hypotenuse. So this side is going to be 9 minus x squared using Pythagoras. So therefore, when you rearrange it, when you get your final integral, remember with the sine, that is double angle. You can use double angle formula, and then you can find a value for sine and cos. So therefore, your final answer is going to be this result, like so. And as mentioned on the previous slide, here, if you have to do sec, it's going to be kind of nasty with domain restrictions and stuff, but